Assalamu alaikum warahmatullah. Hello guys. Today we will write deep feedforward networks and we will solve two big problems. And we will write from scratch the neural network. It is multi-layer perceptron and we will solve exclusive OR problem and we will try to build classification model using this feedforward architecture. So let's get started. Let me to share my screen. Okay. First of all, terminal. We will say Jupyter notebook. Okay. Let me to close this one. It's not related. So, okay, let's get started. Desktop. New. Python kernels. Let's say it multi-layer perceptron from scratch for exclusive OR and iris dataset. Okay. So in previous session we talked about this multi-layer perceptron, that it changed and it boosts the development of deep learning, because they solved this exclusive OR problem which linear models cannot solve. So let me to remind you what is exclusive OR problem. Exclusive OR problem is problem where you are given 1, 1, let's say for 0, 0, you are given 0 and 0, and your function or your model should return 0. If your function is given 1, 0, it should return 1. If your function given 0 and 1, it should return, yes, it should return 1. And then if it receives 1 and 1, it should return 0. In fact, linear models cannot solve this problem. If I do like this, okay, yeah, kind of clearer, I think. So that's exclusive OR problem, and now we will build our neural network, not big one, very simple one, and I will explain you this feedforward process, backpropagation process, and this loss function. We will choose loss function and we will play around, and let's go. First of all, let's import what? NumPy, our old friend NumPy, and then I will say np.random seed42 just to make sure that you can use my code also. And what we need is learning rate, it is 0.1, let's say, and epochs. Let's choose 1000. I think 1000 is pretty enough. So we initialized our learning rate, epochs, how many times we will process, and yeah, we give this random seed. What we need else? So as you know, we have weights bias in each layer, and we have in each layer activation function. Let's write the code, function code for these activation functions. For this we will use ReLU and sigmoid function. Def ReLU, we will receive z. If we receive z, ReLU is what? We will say np.maximum, and I will say z or 0. This is how ReLU works. And for backpropagation, I need to write a function for ReLU derivative. Z. And for ReLU derivative, it is return. I should say the return, I forgot. Return np.where z is equal to then 0, it should return 1, else 0. Then, okay, we implemented ReLU and ReLU derivative. We need now to implement sigmoid. In sigmoid, it's, you know, like it is the boundary of sigmoid is always 0 and 1. And in sigmoid, it is return 1 divided 1 plus np.exponential of minus z. and z sigmoid. And lastly, last but not least, sigmoid derivative. And sigmoid derivative is z multiplied 1 minus z. Okay, now here we have a learning rate, epochs, we have activation functions. What we need else? We need initial parameters. So we should initialize bias, we should initialize weights, and to give them small positive numbers. So before doing that, before doing that, let me to build this dataset, small dataset, np.array x equal to np.array, and it is 0 and 0, 0 and 1, 1 and 0, 1 and 1, okay. And y is np.array, and it is, in the first case, if our model receives 0 and 0, it should give what? It should give us 0, right? In second case, it should give us 1. In third case, 1. And lastly, it should give what? 0, right? That's correct. And we have our data set. And input layer neurons. As for input, our model should receive two things, two values. I will say 2. And our now hidden layer neurons. As in hidden layer, let's select 4. You can select 3 also. 3 is also valid. 2 seems invalid. We will talk about later, you know. Input layer, hidden layer, and then let's choose this output layer. Output layer neurons. As output, we should receive only one result. So like we receive 2 and we give 1, 2 and 1. Okay, I mean 1 output, not number 1 here. And now let's build these initial weights. So I will say hidden weights is equal to np.random.uniform, and I will say the size is equal to what? Size is equal to the input layer neurons and hidden layer neurons. So like that, and then hidden bias is equal to np.zeros. I'm using zeros, but zeros and really positive small numbers, they seems to be the same. The effect of them are the same. So in zeros it is 1 and what? Yes, hidden layer neurons. And now output weights is equal to np.random.uniform, and the size is equal to hidden layer neurons and output layer neurons. I hope I am writing everything correct, there is no typo. Then output bias. Output bias, I am also using np.zeros, and I'm giving 1, and output layer neurons. Yeah, that's all. So what we did, we initialized initial weights, because we will train this, how can I say, we will improve these weights and biases, and by using these weights and biases, which are considered as parameters, we will have a model, neural network model. So we will now run this for loop, the most important part. Okay, so for epoch in the range epochs, okay, we have this epoch, okay, epochs. So for each iteration in range of 1000, right, 1000 iterations, we will do what? We will go forward, we will calculate loss function, and by using this loss function, this error, we will go backward and update the weights. And again, go forward, backward, forward, backward, forward, backward, and it is, you know, like, it is science. Feed forward process. So in feed forward process, hidden layer input. So what is that? It is what? We will multiply the given data x to the hidden weights, and we will add bias. So np dot it is x and hidden weights, yeah, and plus hidden bias. So now hidden layer activation. Now it's time to activate. So now we will use what? ReLU and hidden layer input. So we calculated this hidden layer input with x and hidden weight and bias, and then we will use activation function, and we will, like, this is a result of the hidden layer, and then we will calculate the output layer input. Output layer input, and it is np dot, yes, instead of x it is hidden layer activation, and it is output weights plus output bias and output and prediction, and predicted output is what? So now we found this output layer input. Now we will use another activation function. In this case we will use sigmoid, and I will say output layer input. Okay, is it same? I think the same. So now the predicted output. So now feed forward process is finished. So we went from the beginning, from the input layer to the output layer. So now let's calculate the loss function. So here let's use MC, mean square error, and error is what? Y, the Y true minus predicted outputs, and mean square error is equal to np dot mean square error. Okay, here error. Now we are calculating mean square error, and it's time for back propagation. In back propagation, we will follow chain rule, and by following chain rule, we will update, we will calculate the gradient, and we will update the weights respectively. So derivative of predicted outputs is equal to error multiplied by sigmoid derivative of predicted outputs. So we have this derivative of predicted outputs, and now let's calculate the error hidden layer. Derivative of predicted outputs dot of output weights transpose, and derivative of hidden layer is equal to error hidden layer multiplied to ReLU derivative, and we will give the here, instead of predicted outputs, we will give here hidden layer activation. Yes, activation. So we have here derivative of predicted output and derivative of hidden layer. And now we will update the output weights. We will go from back, okay? Output weights is equal to what? Output weights plus learning rate multiplied to gradient. So here our gradient is so plus hidden layer activation dot t dot dot, and what we will give derivative of predicted outputs. And by using this, we're using learning rate and we are using the gradient, we are calculating gradient and we are updating the weights. Next, output bias is equal to output bias, previous bias, plus learning rate multiplied to np.sum the predicted outputs, and we will use x is equal to 0, keep dimension equal to true. And now we updated output weights. We're almost done. Now we will use hidden weights. Hidden weights is equal to hidden weights plus learning rate multiplied to x dot t dot derivative of hidden layer. And now lastly, hidden bias is equal bias is equal to hidden bias plus learning rate multiplied to np.sum of derivative of hidden layer, x is equal to 0 and keep dimensions equal to true. Now I think we almost implemented the architecture and the process. And lastly, if epoch divided by 100 is equal to 0, I will say print f, and I will say, I will say epoch. This is enough. This epoch will print, what it will print. I will say note. It will print epoch equal to some number, maybe 100, okay? It will literally print like that. Epoch and mean square error equal. So we have epoch, we have mean square error, and in the end of the day, I want to see this predicted output. Print predicted outputs. Okay. Bismillah, let's see. I think maybe error, maybe no error. Okay. Congratulations, guys. So we are almost done. So we are going from each epoch, and you can see in the beginning we have this mean square error of 0.30, and it's 25, and it is reducing to 0.01 in epoch 900. And in the end, you can see the predictions. Predictions are not integers, they are float, because we are using sigmoid. And here you can see that our y should be what? 0, 1, 1, and 0, right? Here, 0.1, if we round it, it will be 0. Correct. Second one, 0.9, it is 1. If we round, it is 1. Next one, 0.9, it is 1, right? And lastly, it is 0, and it is 0. So our model successfully learned and solved this exclusive OR problem. So what we did here is that we are using one ReLU function in hidden layer, and we are using sigmoid in the output layer, and we are using how many? We are using 4 neurons, 4 units in hidden layer, and we are using 2 units in input and 1 in output. If I put here 2, I noticed that 2 is not enough for this model to learn. For example, you can see here the outputs. Now I put 2 here, and outputs are, you know, the error is not decreasing, the mean square error is still the same almost, and the output, you can see it's like 0.5, 0.5, 0.5, 0.5, which is what which means that our model failed to learn. If I use here, for example, 3, our model kinda learns, and now you can see it's 9910. So that's it for exclusive OR. Now let's get started with iris dataset. Okay, let's not spend much time. So what iris dataset? It is classification problem number of labels classes equal to 3, and what it is tabular data is tabular, not image. Okay, we need to start with very simple one. And in iris dataset, first of all, let me to import necessary libraries from sklearn datasets, import iris, import load iris, it should be like that, and then from scikit-learn model selection, import train test split, and from scikit-learn.metrics import accuracy score. I think everything is good. Okay, it's saying from. Okay, yeah. So now let me to load the iris dataset. So iris is equal to load iris, and then x is equal to iris dot data, y is equal to iris dot target, and then I will use encoder. I need to use encoder, one hot encoder, and sparse output, let's say it's equal to false, and y is equal to encoder dot fit intercept. If I don't mistake, I will give y dot reshape -1 and 1. It should be y. One hot encoder. Okay, I forgot to import that, you know, from scikit-learn.preprocessing. Scikit-learn is amazing library, amazing. Import one hot encoder. Check. One and intercept. Fit and transform to transform. So initially our y was what, you know, it was like 1 2 3. I think like it was like 0 1 2 1 2 1 0, something like that, you know, which means that 0 means first class, 1 means second class, 2 means another class. But we changed its representation as kind of encoder, as one hot encoder, where 1 0 0 means first class, 0 1 0 means second class, 0 0 0 0 0 1 means last class. Okay, we just changed this representation. And why we changed this representation? It's just because it is much more easy for our model to teach that this is y, this is classes. Okay, now we have that one, and let me to split x train, x test, y train, y test is equal to what? Train test split of x and y, and we will say test size, if I don't mistake, 0.2 or 3. It doesn't matter. And random state is equal to 42. And let's get started. Okay, now we have split our dataset so that we will train model on train dataset, and then we will evaluate our model in test. Actually, we call this validation dataset, but it's valid for our process also. So now it is process to train our model. What we did in previous exclusive OR. Yes, we initialized seeds np.random seed 42. Actually, we don't need to do that, but for sake of completeness, np.random seed, and we now let's say learning rate. Let's initialize the learning rate. Let's select for this 0.01, and then epochs 10,000. And what's next? So we should initialize ReLU, because we want to use ReLU, but you can use another activation function also. Let me to import this ReLUs. We will follow the same process. It's almost the same. Okay, we will use ReLU derivative, and instead of sigvoid, because our classes number of our classes is not 2, which is not binary, we cannot use sigmoid, unfortunately, but instead we will use softmax. And we don't need softmax derivative for our calculation of backpropagation process. And softmax, what is softmax? Softmax is equal to exponential, equal to np dot exponential, and where z minus np dot maximum, z x is equal to 1, keep dimension equal to true. And we will find this exponential, and then we will say return of exponential divided by np dot sum and exponentials, x is equal to 1 and keep dimensions equal to true. So it's like that. I think we are good to go. Yeah, so we have ReLU, we have softmax. Now we have dataset. What we need? Initialize weights. Yes, we should give initial values for our parameters. Our parameters are weights and biases. So to do that, I will say before input layer neurons equal to what? Xtrain dot shape dot what? In Xtrain, if I will use shape 1 means number of rows, shape 0 means number of rows, shape 1 means number of features. So I need number of features, and hidden layer neurons, I'm using 10. You can change it, you know, like you can change everything here. We are doing experiments, we are learning, you know, like it is very, like, you should have a fun with these models, right? So be curious about every aspect of this. So input hidden, and now output layer neurons is equal to what? Our y train dot shape 1. So again, hidden weights equal to np dot random. Let me to just bring it. Okay, let's not waste time. So hidden weight np dot random size input layer neurons, hidden layer neurons, hidden layer neurons, hidden layer neurons, output neurons, and like that. We can change it to np dot random dot uniform, okay, note, okay, okay. Let me to print hidden weights, because this is our weights. I think we are on the right path. So we have activation functions, right? Yes. We have initialized the initial weights and initial biases. Yes. We have number of epochs, how many times we will process. We have learning rate. We have dataset. What we should do? We should write now this for loop. For epoch in range epochs. The same in exclusive OR problem. The same, we will do the same there. So what we will do simply that we will go with to forward propagation, and we will calculate this loss. We will use log loss, and then we will go to back propagation. Okay. Yeah, it is very interesting, you know, guys. I'm very excited to write this code. So epoch, range of epochs, forward. So what we did in exclusive OR, we calculated hidden layer input. It is np dot. We are giving x train with hidden weights, and we are giving hidden bias, and then we are saying hidden layer activation. It is equal to what we are using here, ReLU, and we are saying ReLU will receive hidden layer input, and then output layer input is equal to np dot. We will give here hidden layer activation, and then output weights plus output bias, and I will say predicted outputs is equal to what? We should use activation function. Here I will use softmax, and I will give to softmax output layer input. And by using this, I calculated the predictions, softmax. So now let's calculate loss function. What is our loss? Our loss is equal to, so we are using log loss, and here log loss is equal to np.mean, and np.mean, np.sum, and y train multiplied to np.log of predicted outputs plus very small number 1e minus 8, and x is equal to 1, and our error is equal to y train minus predicted outputs. So we calculated our loss function, we calculated this error. So in loss function we are using this very small number because these predicted outputs might be 0, and this logarithm can cause some instability. So instead of to prevent that thing, we are using this very small number. And okay, here we calculated forward propagation, we calculated loss in the forward, and now we need to go back by using this chain rule and update the weights. So what we will do now is that derivative of output weights is equal to hidden layer activation.t.error, and I will divide this xtrain.shape 0. And let's calculate derivative output bias. I'm directly calculating the gradients. Bias equal to np.sum, and error x is equal to 1, keep dimension equal to true, and divided by xtrain shape. Output weight, output bias, and let's calculate the error of what? Hidden, yes, layer. Error of hidden layer. This is, we are going by chain rule, and it is equal to error dot dot, and we will use output weights dot t, and then multiply to ReLU derivative, and for ReLU derivative we will say hidden layer activation, and we have this error hidden layer, and we will calculate the gradient for hidden weight equal to what? It will be x train dot t dot error hidden layer divided by xtrain dot shape 0, and derivative of hidden bias equal to np dot sum of error hidden layer, yes, x is equal to 1, keep dimension equal to true, and I will divide to xtrain dot shape 0. I think we could replace this one with one number. So derivative of hidden layer, and now what we need to do is update the weights and biases. So I will say output weight is equal to what? It is output weight is equal to output weight plus learning rate multiplied to derivative of output weights. Output bias is equal to output bias plus learning rate multiplied to derivative of output bias, and hidden weights is equal to hidden weights plus the learning rate multiplied to derivative of hidden weights, and then multiplied to derivative of hidden weights, and then last one is hidden bias, right? We need to update this. Hidden bias is equal to hidden bias plus the learning rate multiplied to derivative of hidden bias, and I will use this if epoch is equal to 1000, because we are using 10,000 right here, because we are giving 10,000, like 1000 is good. If we divide it modularly to 10,000, 2000, and we are receiving 0, please Python print the epoch number and loss, right? Yeah, loss. And in the end of the day, print as predicted outputs. Print predicted outputs. Let's go. Okay, we are having error. Okay. X where? Okay, line 14, exponential. Okay. Okay, I see. So we are having error here. Exponentials. Let's try again. Okay, it's saying output bias equal to learning derivative of output bias. I see. Output bias plus equal to learning rate. We couldn't broadcast output operation output bias. Interesting. Let's check it out. Output bias, the output bias, np.sum error. I see. So here axis should be 0. Sorry, axis should be 0. Let's check it out. Okay, now we have something. We have something. So let me to explain it. We trained our model for certain epochs. First we have 1.44, and then it goes to 0.15 and 0.9, and it goes to 0.06. After these 5,000 iterations, the model is almost stable, not learning after that. The loss is decreasing in that point, like in first 5,000. Which means if loss decrease, it means that our model doing something good, you know, our model's kind of learning. And this predicted output is this matrix. Here we can see this 9.99, 9.610, 9933, 4.2, 9999. Okay, here we are having predicted outputs, but for example here what I will do is that I will take maximum from each index, and for example from here I will say this is maximum, and I will say that the first one belongs to class 1, and here in second one I will say this is maximum, and we will go to class 1, and in the second one the column second is maximum, and it will go to column 2, class 2. So these are our predictions, which are also float numbers. So now what's important is now let's test our model on X test. Okay, we have test dataset. Okay, we have trained dataset. We trained our model in this trained dataset, and now we need to train on this test dataset. So it will be nothing but this one. I will give X test and predicted test outputs. Okay, we have test outputs. Okay, predicted test outputs, and now I will say y hat is equal to np.argmax of predicted test outputs. X is equal to 1, and y test argmax is equal to np.argmax of y test x is 1. Okay, so if I check y hat, it is numbers, right? Y test argmax, it is also numbers. And now what I will do is that I will use accuracy score, and I will say y test argmax, and I will give y hat. Voila! So our accuracy is 0.96. Congratulations. So guys, I think that's enough for today, and we talked about exclusive OR, and we talked about iris dataset, and now like you can easily play. We can easily play by changing this number of hidden layers. Maybe let's use 5. If we use 5, it's also learning. See, it's also learning, and we can check the results. Accuracy score is like like 100% here. So it's like that. We can play around with this thing, or we can say here np.random uniform 0.np.random uniform, and I will say size equal to this thing, and we can again play around. Check. Okay, here like that, you know. That's it about today. Yeah, that's it about today. You have seen this practice of solving exclusive OR problem in simply Python and NumPy, and you have seen how we used this forward propagation, loss function, and a back propagation process for training a model by using like simple framework, NumPy and Python. Of course, PyTorch, TensorFlow, and other deep learning frameworks are much more better, much more easier to use. And it is just to show you how it works, and I hope you have a fun. Please write in comments and enjoy and have a good day. Bye bye.